Thanks to Gertz, I borrowed Gert's little thumb thing, it's been great. It gets offline a couple of times. Yeah. There we go. So if my robot is a little uncertain, then the ends of my gripper are also uncertain. They're fixed, right? So if the robot moves around, it means the end of my grippers are going to be somewhere within those yellow dots. So I drive forward. The dots are going to go somewhere over that area, right? Because that's what the standard deviation tells me. Well, remember, we only looked at one standard deviation. That yellow area represents one standard deviation's variation on this graph. It tells me only 68% of the time is my gripper going to be within that space. That leaves me 32% of the time when it's even further out, right? 32 is not really good, but I've still got a little bit of margin error there. Maybe I'm lucky and this might work. So we can tackle this from another perspective. I can calculate what is my margin of error. How far away can my gripper be from the center and still not bump into the thing I'm trying to grab before I grab it? So with these measurements, 0.35, we've got 0.4 gap, right? That I could be either 0.4 to one side or 0.4 to the other side, and I'd be able to get past and grab my object. So we can ask the question a different way. I want to be much more certain than 68%, right? And I've got a margin of error of 0.4. What standard deviation should I have before I attempt to do that gripper, right? How reliable should my estimate be? Well, first, before we do that, let's just look at the extreme. Right? If we take the same standard deviation here, we say, okay, my margin error is 0.4, what's the probability I'm within 0.4, right? So I'm just going to touch at the worst case there. So I get 81%. It's not too bad, 81% of the time I'm going to get there, I'm going to do that. But what that tells me is there's 20% of the time where my robot is further away than that and is going to hit that thing before I pick it up, right? 20%, that's 1 in 5. That sounds like tabletop challenge demos to me, right? So what we saw earlier, we all thought, yeah, that was great, go ahead and grab it. But this is telling you 1 in 5 times you're going to fail, you're going to bump into your object before you grab it, right? Because we didn't interpret the standard deviation properly and come out. That's probably pretty noisy, maybe my robot's better than that. How good does it have to be so I can be 99% confident that I'm going to grab that, right? We need to go 3 standard deviations. So 3 standard deviations is 0.4. I want to be within 0.4 99% of the time, okay? So if I calculate what's 3 standard deviations at 0.4, still looks the same, right? I'm not touching it, but now my sigma changed. I said, what sigma do I need? 3 times 0.13 equals 0.4. So this tells me if I drove up there with my Kalman filter and I wanted to be 99% sure of not bumping into that object, I shouldn't try to pick it up unless the uncertainty in my estimate was less than 0.13. Right? If my standard deviation when I drove up and the Kalman filter said, hey, here you are, but you've got this much uncertainty in your position, is that good enough? And I can actually calculate what threshold I should put. How do I ask that question of what is the interval under my graph? You see how I'm putting those lines, 99%, I've captured just about everything. I'm 99% certain if the probability is within that range. So this is kind of the crux. This is how you improve your robot. You interpret that probability and you understand how to use that to make better decisions on whether to act or not on the robot. So having that extra information and using the noise component of the output is super important to being able to get a successful robot. I'll do it over here. Well, unfortunately, going back on these slides, it's not actually slides. So I kind of have to go right back and start through. I'll bring it up later if we want to do some questions. But we're nearly at the end. It will take a long time to go back. So we talked about all those constraints, Kalman filter, linear Gaussian models, and there have been limits. There are extensions of the Kalman filter, one called the extended Kalman filter, what a surprise. And both of these, the uncentered, rumor has it that was named because somebody had some air freshener or something on the desk of the person next to them and he named his algorithm the unscentered. So I guess it tells you what he thought about the air freshener or something. But there are 2 variants of the Kalman filter that deal better with non-linearities. Right? If our real-world robot isn't easily modeled in a linear environment, we probably want to look at using the EKF or the UKF. And in fact, probably most implementations really use these versions. The plain vanilla Kalman filter probably isn't, all the ROS algorithms tend to use the extended Kalman filter. There's no harm in using that. It is more mathematically complicated. It's dynamically calculating the linear model at every step. So it's actually generating the linearization around the current point. Rather than before we had to come up with this general linear that sort of fit every possible condition. We're coming up with a linear model exactly matching where we are right now. So it's doing all sorts of calculus on the fly. It's much more numerically complicated. The uncentered Kalman filter works by, as well as looking at the main probability of the center of where we think we are, it uses the uncertainty in that and then does simulations nearby and sort of says, well, if that was that, what if I was actually here, or what if I was here? And it sort of statistically distributes what they call sigma points and does a whole nother estimate on those points. On the assumption that if I've got some non-linearity or uncaptured behavior, maybe one of these outlier points will catch it better. And then it kind of merges it all, mushes it all back together to give you a final, better update. So they tend to be more robust under certain conditions. They can also blow up worse if they aren't right. They're more numerically, computationally demanding, but as I said, most people are probably going to use extended Kalman filters these days. If you want to go beyond that and get rid of all these constraints, we use a particle filter. That's kind of the granddaddy of all of does non-linear dynamics, non-Gaussian probability distributions. It does a lot, but it uses these sampled particles. So we'll have 1,000 estimates scattered throughout the probability that you're trying to work. So things like SLAM algorithms and that use particle filters. So they're all the same type of estimator. The inputs, the outputs kind of work all the same, but these types of algorithms can handle a broader case of the types of randomness that we're dealing with and the types of models that we have to deal with. So just to recap everything we saw, there's our command. We give our robot commands. We take measurements with sensors. We wanted to get X and just know everything about our robot. That's not accessible, that's the world. We plug in the Kalman filter. It takes our state estimate, simulates how that behaves based on the commands, predicts it, updates it using the math, and comes out with a new state. Key takeaway, states are probability estimates. We have to know how to interpret them. Don't just use mean, do understand and do the calculations to make sure that you can understand how to interpret the uncertainty, the sigmas, the spread of your probability distributions. It's important to be able to do things better. Those who want to dig into it anymore, Kalman's paper's there for the reading, very light reading, don't worry, trust me. For slightly easier to read stuff, there's a couple of other papers there on covariances and Kalman filters. Wikipedia obviously has tons of stuff on Kalman filters. There's some good MATLAB has produced some good videos showing how to simulate and understand a Kalman filter. And more for credit, the software I used to do all the animations was this thing called MANIM from 3 Blue 1 Brown. And if you ever see YouTube math videos, these guys do these amazing math videos out on YouTube, and they make their software available to use. So that was about it, I think. Eventually the whole video that Bill's been making will be put up, and I can post the slides. As I said, that was actually a Python program that I was running. So it's all condensed down into about a 3-minute video that doesn't stop automatically. So I can post that if people want the video. And I said Bill will have the full, I presume Bill got a good video of everything. That will be
I'm going to try pass, sorry
Yep.
to cut you off there. I'm going to try and pass microphones around because it's really hard to hear the questions. So if you have a question, let me know. I'll get you a microphone.
So how do you incorporate multiple sensors for, say, the same thing? Like if you had an accelerometer and encoders, you could compute velocity sort of 2 ways using those.
Right, I mean, I just showed single variable and two variable. If you've got multiple sensors, you just have more rows in that measurement vector, and your A and B matrices get bigger. So there's an equation to calculate every one of them. But they may all contribute to the same output. So whereas I had the diagonal ones, you'd have more ones, because 2 or 3 input sensors would be getting calculated into the one state output vector. So that the A and B matrix get a little bit more complicated to mix that together. But the covariance is just, the diagonal gets longer, there's a covariance for every single sensor, so the matrix gets bigger. The model has to incorporate how do you actually calculate what to do with those, so that the model equations get a little more complicated, but it's just more of the same, basically.
Mm-hmm. Okay.
So if your noise is not Gaussian, but can you use mixture of Gaussians?
That's a different algorithm, basically. But that's kind of what the uncentered Kalman filter is doing. And it's taking multiple Gaussian distributions around the center one. But yeah, if you have other things. I said that it was the optimal algorithm with Gaussians. Doesn't mean it doesn't work if they're not Gaussian. It doesn't work as well, and it may not be the optimum. That means that you could find a better nonlinear algorithm that dealt better with the nonlinear, but the Kalman filter may still sort of work. Right?
When you describe these different algorithms, there's this, extended and whatnot, and then the point you described at the very end. It sounds that these sound computationally intensive. And I guess what sort of computational load do you have for an average hobby robot? I mean, do I need an Arduino? Do I need a Raspberry Pi 4 or 2 of them? What do I need?
My first slide, well, not my first, but in the bio of Kalman, remember I said that the first implementation of the Kalman filter was on the Apollo navigation computers. They had 2K of memory, and they implemented Kalman filters on it, right? Plus everything else to get the rocket to the moon and back.
Yeah, but they were real rocket scientists.
True. But we're roboticists, right?
This is brain surgery.
Yeah. So the plain Kalman filter depends on the number of variables. Basically, it's just the matrix math. You saw it. All it's doing is a bunch of matrix math, and it's how does matrix size? The more variables you have, the bigger the matrix get, and what a matrix scale with the square of the. There's one inversion, which I think is the cube. So there's a little bit. So if you get giant matrices, yeah, it starts bogging down a little bit. But for 5 or 6 parameters, velocity, x, y, it's probably not too big. Certainly, there are definitely Kalman filters on Arduino. I mean, what sort of update rate do you get? Steve, do you have a?
Yeah, there's a number of sensors in the past few years that are doing basically inverse computation, sensor fusion,
Right.
on like a Cortex 3 or M0.
Right. I think there's even implementation on the latest like M4 microprocessors and stuff like that. So,
Bosch, the 55 IMU.
yeah, they have Kalman film that built into the chip. So it's not exorbitant. That's what's good about it. Things like the particle filter are huge. Yeah, you need thousands of particles. But while the Kalman filter is very popular, it's actually relatively computationally simple to use. You have any more questions?
Right there.
Thank you for your presentation. For people who would want to implement this into their own hobby robotics, but are slightly daunted by the amount of knowledge base that goes with this, what would you recommend where we start if we wanted to implement the Kalman filter? For instance, we were wanting to do more improved path planning for robots. Would you recommend we start with like the open library? Would you recommend that?
I mean, I definitely recommend finding a library that implements it. Don't try to write your own. So OpenCV has Kalman filters. Python NumPy has Kalman filters. Just about every vaguely math algorithm out there, library out there will have an implementation of it. So definitely look around whatever platform you're on. You'll
In
find
terms of
something.
evaluating it on our own end as well, making sure that we can get to a point where we can say, okay, well, based on the amount of signal input that we're getting and the expected result is supposed to be like this, what is the, how would you recommend we evaluate it on our own end?
How are you?
Our use of it.
Is your robot better? Did you improve your robot with your Kalman filter? I mean, so you need some sort of baseline. How does it behave without that? I plug in the Kalman filter. Is it getting better? I mean, something
So you increase, in the table box challenge, you increase your standard three standard deviation, you know,
Right.
99% confidence, and I guess it depends on, I mean, okay, so I want to go after, if I'm going for that 99%, the robot may never move forward and attempt or try, you know, to, that's the point here, is that you loosen up that probability.
So that, I mean, it points out that that is now it becomes your decision.
Right.
It's no longer, oh, it was the battery, so I've got a loose wire, oh, it's the sun's
Well,
in
if
the
I'm
wrong
waiting
spot.
for 99%, my robot might, you know,
Right.
I'll never give it the forward command.
Right, so
I go
it's up to you
two
what,
standard-
but at
I'm
least
gonna
you
bet on
know,
the 68%.
at least you know
I'm gonna go
what
for
your
it.
probability of failure is.
Got it?
And it's up to you to decide is that good or
Well,
not.
I'll roll the dice on 68% all day long. Dave?
Okay, that's first.
Yeah, so that was basically also my question. So my robot is on the table looking at that object and sigma is not good enough. So what can I do? Can the robot do something to make it better?
Well, I mean, maybe you just need to drive around a bit. Maybe you got some noisy measurements on the way getting there the first time, so it tells you, okay, I've got to try to localize a little bit better. You'd have to obviously characterize what is the best my robot can do, and there's going to be some bound on that you'd know about. So you'd have to set your own expectations by probably testing it and seeing how good am I. Other than that, you're probably looking at better sensors or
Yeah,
better control algorithms.
In my testing, I saw that it can do better, and at this point it is bad, so I know that probably if I drive
Right,
around and get some measurements, then
Right. Yeah,
probably at the
typically
next approach I will maybe get it.
better sensors, better actuators, put a better control system.
Okay.
Possibly, if your model is pretty loose, you can get better results by trying to improve the model. You know, the simulation might help, but basically it's telling you though, this is how reliable your robot is, and you have to say, is that good enough for me? Do I need to improve the software or whatever?
Or maybe drive around.
Or drive around, maybe you set a
Drive
bumper
around
way
less.
there.
If you're going slower, maybe you have less error in your
Right,
measurements.
so I mean, you generally characterize, I would know typically how accurate my robot would be, and I would attempt things that it's capable of doing.
Slow down.
And if I get somewhere where I've some reason, see I've got a lot more noise than I normally do, I know I need to back off and reapproach, and I'll get a better estimate this time. There was some questions over here, I think.
Dave's got a question.
Dave, yep.
I had one. It is working. It seems like one of the interesting ideas inside all of this is that you can improve performance from multiple sensors by waiting. If you're trying to do an estimate, you might say what to do next. Then you say, well, I've got several different sensors that have several different values, and that the Kalman filter says you should weight those values by inverse sigma, if you will. So essentially, you give more validity to the least noisy.
That's kind of what it's doing. If you've given it the right amount of R, or if you told it R and to characterize your sensors, it's going to favor the least noisy sensors. But one thing I talked about, the iterative loop that we just constantly do it, it's actually possible to run the updates and sensor inputs at different rates. And you can do that for different sensors. So you don't always, on every update, you don't have to process every sensor. So you've got some sensors that are slow, you only incorporate them when you actually get new readings from them. And if you get fast sensors, you can iterate on that more quickly. So there are kind of variations you can apply that to as well.
You kind of touched on it already between the time I had an idea and the time yeah, drive around. I've run into issues, and just as a note about how do you get better estimation for standard deviation, things like that. I've run into bugs in some visualization libraries where if you're looking at the thing at the wrong angle, sometimes it'll spit out nans. So the answer is really just drive around. Shift your view half a degree,
Right.
and suddenly the library just kicks in to making sense again.
Right. I mean, you bring up a point there, Steve, that as well as having the multiple rates, you can do failure data. If you've got multiple sensors, you can do failure data. If I detect that my sensor is failing, whack in a big standard deviation, and the filter's just going to ignore that faulty sensor. right? It gives, you can do things like that, make it fault tolerant by having some way to detect if sensors are failing. You can just map them out by changing the covariance matrix or the variance on that particular sensor.
I did have a question, and this is kind of like half-formed, because I'm not entirely comfortable. I mean, I'm getting better at the math for this, but this loop, this update, and the parameters look very much like some of the machine learning that I've used, and I'm wondering if there's ways to maybe optimize this through like a reinforcement learning system.
If you had a way to learn that model Q covariance or your sensor, yeah, I mean, anything that can help you estimate those would be useful. Now, I mean, something as, we talked about the kind of basic statistical probability. There are probably at least 5 different ways you can derive a Kalman filter. There's an instance of Bayesian inference, with the optimal least squares error estimator that we kind of approached it from. There's whole different branches of mathematics that all come up with the same algorithm, and they try to derive an optimum solution in whatever framework of mathematics they're looking at. So it's very interesting that there's so many different ways of looking at it and applying.
I was wondering if you could comment on the size of your state space model, where you can have kind of constant velocity, assume that you have constant velocity or constant acceleration, and like how that trade-off is with result.
Things like velocity versus acceleration, it depends on the model. I mean, I showed that example there with the holonomic. It was just 4 states, right? Position and velocity of x and y. I didn't put any accelerations in there. You can model acceleration if you want to.
So you assume constant velocity. Velocity, like, it's basically something that's in motion that's not going to generally
change. The model would be simple, right? The dynamics are simple there, right? Nothing's changing the dynamics.
So if you have acceleration, then you assume constant acceleration, but your velocity.
Right. Yeah. Now, one thing, I came up with that really simple model with all the ones, but it made kind of an assumption. It made the assumption that I told my robot to drive at 1 meter per second, and it was going to drive at 1 meter per second. So there's an assumption there that underneath the Kalman filter, there's a control system. Taking my command as a speed control on the motor, that's pretty good. I mean, we know we're never going to exactly track a velocity command, but it made the assumption that the dynamics are simple if there's kind of a lower level control system making the dynamics simple, right? Taking care of the real physics. We didn't have to model the current in the motors and the torque on the wheels and the accelerations and all that. So we just assumed there's a pretty good control system that's going to track my velocity pretty well, and then we can just model it much more simply at the higher level. Okay.
But you could have a force-driven device and model that and have a Kalman filter operate.
Right. I mean, the constraint is, can you model it linearly? Is there a good linear approximation to your model? And then pretty much, yeah, you can take whatever state information you're interested in, accelerations, velocities, angular velocities, torques, all that could be part of your state space if that applies to whatever machine you're trying to track. And you can try a good linear model of it. Things like differential robots actually cause problems, right? Because differential, you don't have independent control of x and y. So there's correlation. And you can't actually move y. There's actually a non-linearity in y. So you can't actually create a linear model of a differential robot. So this kind of fudges people do when they put linear differential drives into things like this. Because that is a good example. Anything that has sine and cosine, that's not a very small angle of movement, is non-linear and causes all sorts of problems. So there's ways to, tricks you have to play to get around that sort of thing if you want to model it that way. Okay.
Any other questions?
Well, all right, thank you very much, everyone.
Yeah, thanks a lot, Ralph. So thanks everybody for coming. We have this room until 10 p.m. So for what we call random access, general socializing, after 10, you can continue talking outside in the parking lot. Again, thanks for coming. We'll see you next month.